Okay, so continuing to work with the moment of inertia of an area. Let's take a look at another problem. 683. This is on page 305 in your text. Here they want us to determine the centroid location, y bar, of this irregular shape, and then calculate the moment of inertia of this area about the axis. Okay, so using our tools from the beginning of chapter 6, let's model this shape as a composite of multiple shapes. So we can see this. We can model as a collection of three rectangles. We'll say 1, 2, 3. With the dimensions given, I believe this height is 250 millimeters. This width here is 50 millimeters. Likewise, 50 millimeters on this side. This height here as well is 250 millimeters. And its thickness here is 50 millimeters. So to find the centroid location, we set up our table, segment, area, which will be in millimeters squared, y wavy bar was the coordinate of the centroid for each composite shape. Then our y wavy bar a times area, which would be millimeters cubed units. So setting up this table, we have three segments here. So the area then of the first segment, segment 1, will be the 50 millimeter thickness times the 250 millimeter height. The location of the centroid for segment 1, and with this being a rectangle and using our Appendix B tools, and with this being our x-axis here, so from that going upwards, the location of the centroid would be half of 250, because the centroid, according to Appendix B, a rectangle is directly in the center. So this would be 125 millimeters is the coordinate of the centroid in the y direction for segment 1. So then y wavy bar, this would be 125 times 50 times 250. Likewise for segment 2, the area is once again the thickness, 50 millimeters, times the height, 250 millimeters. The location of the centroid in the y direction from the x-axis is in the center for it being a rectangle. So this once again will be 125 millimeters. And then the area times the y wavy bar will be 125 times 50 times 250. Then last but not least, segment 3, the area would be the thickness, 50 millimeters, times the length of segment 3, which would be the total length of the shape, 350 millimeters, minus 50, which would be 250 millimeters. The location of the centroid here, once again, we're right in the center, so it'd be half of 50 millimeters, so it'd be 25 millimeters, and this is just multiplication. Sum this up, we have our area This comes out to be approximately 37.5 times 10 to the 3 cubic square meters. And our y wavy bar A, summing all three of these, comes out to be 3.44 times 10 to the 6 millimeters cubed. So then our y bar is our sum of our y wavy bar A over sum of our areas. So it's 3.44 10 to the 6 millimeters cubed over 37.5 times 10 to the 3 millimeters squared, which yields approximately 91.7 millimeters. So that is the location then of our centroidal axis of this irregular shape. So basically, this distance here will be our y bar. So that's the first part of the problem. Next, let's redraw a shape right quick. We said consists of 3 rectangles. One, two, three. This being our x-axis, and we calculated our y bar distance. So the location of our x prime axis, this distance here is y bar, which we said was 91.7 millimeters. So then to calculate the moment of inertia about this axis, we have to use our parallel axis theorem, which involves the equation I sub x, I bar sub x, plus the area times dy squared. So we can set this up in one swoop, or we can do it in tabular format. If we do it in one swoop, we'll just do it that way. It's a pretty clear way of doing it. So if we say segment 1, I bar x, we'll say sub 1, segment 1, will equal to, now appendix B for a rectangle, I sub x, go to that in your textbook, which is page 814 through 815. I sub x is for a rectangle 1/12 base height cubed. So I bar sub x for the first segment be 1/12 times the base, which is, this is 50 millimeters, this is 50 millimeters. The height we said was the total shape 250 millimeters, and this thickness here was 250 millimeters. Okay, so for segment 1, 1/12 the base, that's 1/12 of 50 times the height cubed, the height being 250. Then, using the parallel axis theorem, let me highlight this, parallel axis theorem. Then, plus the area, which is base times height, 50 millimeters times 250 millimeters, times dy squared. Now remember, dy is the distance from the composite centroidal axis, which we said was 91.7, and the centroid of each individual shape. So it's just the difference or the distance between those two axes squared. So in this case, it would be the centroid of segment 1 is located at 125 millimeters. And the composite centroid is 91.7 millimeters from the x-axis. So let's write that down. So that we says the difference here, 125, which is the central location of segment 1, minus the y bar, which is the central location of the total composite. This is dy squared. All right, so then let's work segment 2. We'll say I sub x2. So then once again, for a rectangle, it's 112, the base, 50 millimeters, times the height cube, height being 250, plus the area, 50 millimeters, times the height, 250, times the dy squared, which once again, for this rectangle, the centroid of that segment 2 is half the height, because for a rectangle, the centroid is located right in the center. So it'll be 125 minus the location of the x prime axis, which is y bar from the x-axis, 91.7 millimeters, squared. That's your dy. Segment 3, we'll say I sub x3. This is the bottom rectangle. So once again, for a rectangle, 112 from appendix B, the base. Here the base is 250 millimeters, and the height being 50 millimeters cube, 112 base height cube, plus the area, which is 250 times 50, times dy. Now we said dy is the distance from the composite centroidal axis, which is x prime, which is separated from the x-axis by y bar. That's 91.7. It's the distance from that and the location of the centroid of the individual shape. And for the rectangle, once again, right in the center, in the y direction, that centroid is located 50 over 2, which is 25. .25 millimeters. Squared. So this term is your dy. Let me write that a little bit clearer. This term is your dy. This term is your dy. This term is your dy. So doing this math and then adding for your I sub x, we'll say total. It'll be I sub x1 plus I sub x2 plus I sub x3. Doing this math, working it out, you get it to be approximately 216 times 10 to the 6 millimeters to the 4 power. Take a look at another problem. 684, same page. It says determine Y bar, which locates, like we said, the X prime axis, which goes through the centroid. For this cross-sectional area, and then find the moments of inertia I sub X and I sub Y. All right, so first, we have to find our centroidal axes. So using our tools, let's draw this figure. It's a composite shape. We can consider it to be two rectangles. So this would be segment 1, segment 2. We'll consider our x-axis to be here and begin working. So have our segment. This is in millimeters, so area is in millimeters squared. We have our y wavy bar. This is a coordinate, and so length millimeters. Our y wavy bar A is millimeters cubed. Segment 1, segment 2. Okay, so the area of segment 1, which we said would be the top rectangle, that is the 20 millimeter thickness times the 75 plus 75 length, which is 150 millimeters, base time height. The location of the centroid of segment 1 from the bottom x-axis, we have to go up 150 millimeters to get to segment 1. Remember, this height here is 150 millimeters. The thickness here is 20 millimeters. This width here is 150 millimeters. And this thickness here is 20 millimeters. So to get to the centroid of segment 1, you have to travel 150 millimeters up, plus the center of that rectangle, so then 10 millimeters. So that location will be 160 millimeters. Then y wavy bar A would be 20 times 150 times 160. For our segment 2, the area is base times height, so that's 20 millimeters. Height being 150 millimeters. The location of the centroid of composite of segment 2 would be half of the total height because it's in the center. So it'd be 75 millimeters. Therefore, y wavy bar A will be 20 times 150 times 75. So then the sum of our areas, 20 times 150 plus 20 times 150, 6 times 10 to the 3 millimeters squared. Sum of our y wavy bar A. This comes out to be 20 times 150 times 160. And you got 20 times. This comes out to be 7.05 times 10 to the 5 millimeters cubed. So then our y bar would be 117.5 millimeters. So that means that, let's get a different color. Our x prime, so the difference here, our y bar, that's our centroidal axis location. X prime is y bar away from the given x axis. And y bar is 117.5 millimeters. That's the distance. Okay, so that's the first part of the problem. Now I just wanted to find the moment of inertia about the x and about the y axes, I sub x and I sub y. Let's go to another page, keep working. Let's redraw a figure. Segment 1, segment 2. It's 20 millimeters. 50 millimeters. 50 millimeters. All right, 20 millimeters. So using our parallel axis theorem, I sub x, I bar sub x plus a times dy squared. So for segment 1, which is the top rectangle, let's say I sub x sub 1. From appendix B, for a rectangle, I sub x is 112 base height cubed. (112) times the base, which is 150 millimeters, times the height, which is 20 millimeters cubed. The area is simply base times height, which is 150 times 20 millimeters. Now we have to have our dy squared, which we said is the distance from our, let's draw axes again. We said this was our x-axis. We calculated our x prime separated y bar, which we said was 117.5. So then our dy is the distance from each individual segment's centroid to the centroid of the composite. So for segment 1, our centroid location from the bottom axis is 150 plus the center of segment 1, which is 10 millimeters. So that's 160 minus the 117.5 squared. So for segment 2, say I sub x2, once again, for a rectangle, 112 the base times the height cubed, 112 the base. The base in this case is 20 millimeters, the height being 150 millimeters cubed, plus the area, which is base times height. And our dy here, once again, for a rectangle, the centroid of that individual segment is in the center. So the center of a height of 150 would be 75. So then that the dy, remember this is the dy term here, the dy term would be the 117.5 minus the centroid of the individual composite, 75, squared. Once again, this is our dy term. So then adding these two together, so you'll see I sub x1 plus I sub x2 for a total moment of inertia about the x-axis. This comes out to be approximately 16.6 times 10 to the 6 millimeters to the 4. So now we have to do our I sub y. Now by inspection, we said that's our x-axis. This is our y-axis, right? You can see that the centroid of our composite, the way it's set symmetrically, is the same as the centroid of each of the individual segments 1 and 2 due to symmetry. The centroid of the composite and the centroid of segment 1 and segment 2 coincide. So let's say that in writing. The composite centroid, we'll say y prime, passes through centroids of the two segments. So in this case, from Appendix B, I sub y for a rectangle is 1/12 the height times base cube. Let's go to another page. It's from Appendix B. So then we've solved 2/3 of the problem statement. So last part is asking for I sub y. We said, hey, the centroid of the y prime axis passes through the centroid of each segment. Therefore, for this case, there is no dx. Or better yet, dx equals 0. So then our parallel axis simplifies to simply, we'll do it this way. So for segment 1, our I sub y is simply 1/12 the height for segment 1, which is 20 millimeters, times base cube, base being the width, so it's 150 millimeters cubed. And for segment 2, let's say I sub y2, 1/12 the height, which is 150 millimeters, times the base cube, because we do not have to worry about d sub dx. So then our I sub y, add the IY1, I sub y2, you get approximately 5.73 times 10 to the 6 millimeters to the 4. And we've solved the problem. Take a look at a few more. Take a look at problem 6-89. Here, they want to know the moment of inertia of the area about the y-axis. So we can represent this beam as two segments, segment 1, segment 2. This thickness here is 50 millimeters. This height is 250 millimeters. This width is 300 millimeters. And this thickness here, this is 50 millimeters. Given your x-axis location and your y-axis location, once again, due to symmetry, let's say that better. By inspection, the y prime axis passes through the centroids of segments 1 and segment 2. So there is no d sub dx or dx. No dx or dx equals 0. The composite shape centroid is shared with the composite shape centroid was shared with the centroids of each individual segment 1 and segment 2. And that's for y prime. Obviously, our x prime centroid axis would be different, but in the x direction, our y prime centroid axis is shared by symmetry. All right, so with that being said, and the problem's asking for about the y-axis, so it's I sub y, which we know from Appendix B to be 112 height base cube. Height base cube. So for segment 1, the height, which is 50 millimeters, times the base, which is 300 millimeters cube. For segment 2, 112 the height, which is 250, times the base, which is 50 millimeters cubed. So I sub y total is I sub y1 plus I sub y2. This gives you 115 times 10 to the 6 millimeters to the 4. Let's do another problem. Let's take a look at 6-90. Here they want you to find y bar and then find a moment of inertia about the x prime axis. All right. Okay, so this thickness here is 50 millimeters. This total width here is 300 millimeters. The height here, this is 250 millimeters. And this thickness here is 50 millimeters. Okay. This is our x-axis. We'll call this segment 1. And segment 2. So setting up our chart. You have an area. This is in millimeters squared. Y wavy bar, which is millimeters. A, which is millimeters cubed. That's segment 1, segment 2. So the area of segment 1 is base times height. This is simply 50 millimeters times 300 millimeters. The location of the centroid of segment 1 from the bottom x-axis, we have to go up 250 millimeters. Then for rectangles located in the center, so that is 250 plus 25 gives you 275. Is the location. So our y wavy bar A is multiplication 300 times 275. For segment 2, the area is base times height. This is 50, height being 250. Location of the centroid is right in the center, so that'd be half of 250. So this would be 125. And our y wavy bar A is 125 times 50 times 250. Sum of areas. This gives you 50 times 300. Let's do the math right quick. It's 27.5 times 10 to the 3 millimeters squared. Our sum of our y wavy bar A gives you this comes out to be 5.69 times 10 to the 6 millimeters cubed. So our y bar is comes out to be approximately 207 millimeters. So what that means is our x prime axis this distance here is y bar, which we said is approximately 207 millimeters. So that's the first part of the problem. Then they wanted to find the moment of inertia about the x-axis. We know from Appendix B, for a rectangle, I sub x is 1/12 base height cubed. So let's go to a fresh page. So it's 50 millimeters. This height is 250 millimeters. This width here, 300 millimeters. And its bottom width is 50 millimeters. So we know for a rectangle, I sub x, 1/12 base height cubed. So for segment 1, using our parallel axis theorem, so for segment 1, so that's 1/12 times the base, which is 300 millimeters, times the height cube, which is 50 millimeters cubed, plus the area, which is just base times height, times your dy. So we said, it's our x-axis. We'll calculate our x prime axis, separated by y bar, which we determined to be 207 millimeters. So our dy we said is the difference from the individual segment's centroid to the location of the centroid of the composite. So for segment 1, the centroid is located 250 plus half of 50, which would be 275. That's the location of segment 1 centroid from the x-axis. So the difference for dy would be 275 minus the 207. We calculated for the composite squared. For segment 2, once again for a rectangle, 1/12 the base, which is 50 millimeters, times the height, which is 250 millimeters cubed, plus the area, which is base times height, times, so remember this is our dy term. So here, the dy term is the centroid of segment 2, which is half of 250 located at 125. So the difference would be our y bar, 207, minus the 125 squared. And once again, this is our dy term. So our moment of inertia about the axes, one, you do this math, you get approximately 222 times 10 to the 6 millimeters to the 4. So that concludes our lecture for today. If there are any questions, please do not hesitate to email me, and have a safe day.